All right, so now let's analyze and sketch a graph. So within this, we'll even review things like looking for relative extrema and looking for inflection points. So I'm not doing a separate problem with those, but those are involved in here. Okay, so when we take a look at this function here, first thing we want to notice is any discontinuities or even any domain restrictions. Now notice that in the bottom we have the square root of x plus 1. So that means that our domain for this whole function, well, from the square root we can only do from -1 to infinity, and we can't use -1 because that would make the denominator 0. So our domain is only -1 to infinity. So anything that occurs outside of there is just not relevant to this problem. All right, so I'm going to start with some intercepts. So let's look at any x-intercepts. That would of course be when y is 0. So x squared over the square root of x plus 1 would have to be 0. Now that's only going to happen if x is 0 to make the numerator 0. And that would give us the point 0, 0. Y-intercepts, so let x equal 0. Well, then you're just going to get 0 over the square root of 1, which is 0. So y equals 0, but that's obvious because we had the point 0, 0, so it's both an x-intercept and a y-intercept. Okay, how about asymptotes? Let's look for some vertical asymptotes. So we'd be looking for somewhere where we have a limit going to infinity, and one way to look at that is to see if there's a place where the denominator is going to 0 and the numerator is not. And we do have that at -1. Now -1 is not in our domain, but it is important to realize it is a vertical asymptote. Horizontal, this is where we would take our limits going to plus or minus infinity. Now in this case, since we're only defined on -1 to infinity, we only need the one limit, the limit as x goes to infinity of x squared over the square root of x plus 1. Okay, so now notice that we have basically a power of x squared on top and basically an x to the 1/2 on the bottom, which means that we have the top dominating over the bottom. Now we could divide through by x squared, we could divide through by the square root of x, which is pretty much the highest power in the denominator, but I can sort of just reason that the top is going to dominate, so we're going to get some type of infinity. Now as x goes to infinity, the numerator is going to be positive for its x squared, and the denominator squared x plus 1, it'll be positive. So we are going to get positive infinity as that limit. Now it does tell us that there's no horizontal asymptotes, but this is an important fact that we know that as x goes to infinity, the function values go to infinity. Okay, extrema. Well, this is where we're going to need the first derivative. Okay, now so remember our function is x squared over the square root of x plus 1. All right, so it's going to be a little messy. Derivative of the top 2x times, I'll say x plus 1 to the 1/2, which is the bottom, minus the top x squared. Derivative of the bottom would be 1/2 x plus 1 to the minus 1/2, chain rule just gives a 1, over the bottom squared, but the square root of x plus 1 squared will just give us x plus 1. Okay, so if I work with this a little bit, I can see that I have 2x, let me go back to the square root of notation for a minute, minus x squared over 2 square root of x plus 1 all over x plus 1. Okay, So if I were to say multiply top and bottom by 2 square root of x plus 1, I should be able to clean this up a little bit, because when I multiply in the numerator, I'm going to get 4x times x plus 1 minus x squared over 2 x plus 1. Now I have an x plus 1 to the 1 and x plus 1 to the 1/2, so I get x plus 1 to the 3/2. Okay, so that's 4x squared plus 4x minus x squared over 2x plus 1 to the 3/2. So that is 3x squared plus 4x over 2x plus 1 to the 3/2. And so that is 3x plus 4 over 2x plus 1 to the 3/2. All right, so that looks like pretty good here. We're going to ask our two questions. When is f prime equal to 0? When is f prime undefined in our domain? F prime equal to 0, x equals 0. Now, yes, this is 0 when x is -4/3, but that's not in our domain, so let's get rid of it. And it's not undefined anywhere else where, other than where the original function was undefined. Okay, so if we end up putting just our 0, now again, actually I need just a portion of the number line because I'm going 0 to infinity. All right, and I'm going, sorry, -1 to infinity, and then I'm going to put 0 in. And now I can put some values in. This is for f prime here. Go back to my derivative. If I put something between -1 and 0, so like a -1/2, I would get a negative from the x. I would get a positive here, and this bottom thing is going to give me a positive, so I would get an overall negative. And then if I put something like 1 in, I'm going to get a positive, telling me that here f is decreasing, here f is increasing. So we had decreasing, increasing, and so what I see is I actually have a relative min here at 0 something. But we already figured out 0, the value is 0, because if I plug 0 in, I get 0. Okay, so I found a relative minimum there. Furthermore, we saw if we want to record some of this, f was decreasing on -1, 0, and f was increasing on 1, infinity. All right, so let's go to the look for some inflection points and talk about concavity. So we're going to need the second derivative here. So if I go back to the first derivative, and I would probably use some form like this, then you're going to get 6x plus 4 times 2 x plus 1 to the 3/2 minus 3x squared minus 4x plus 4x, the numerator. And the derivative denominator would be 2 times 3/2 x plus 1 to the 1/2, and that's over the denominator, which was 2x plus 1 to the 3/2 all squared. All right, so this is a really, really messy one. Just for the sake of time, I'm going to skip some of the steps in the simplification here. Don't worry, it's not the nicest of problems, but just realize that if you were to simplify this, you could get this down to 3x squared plus 8x plus 8 over 4 times x plus 1 to the 5/2. Okay, again, we'd be looking to see where the derivative is 0, or where the second derivative is 0, where the second derivative is undefined. So now if I put 3x squared plus 8x plus 8 equal to 0, you're going to find that you're only going to get imaginary solutions to that. Plug it into the quadratic formula and see, which means that there aren't any critical numbers coming from there, or critical numbers of the, in this case, zeros of the second derivative. And there aren't any places where this second derivative is undefined where the original was defined. So that's done. So we actually don't have any points to put on our chart except for, just our domain here. And the reason is that if you look at this, for anything bigger than -1, this is always going to be positive, meaning this function is always going to be concave up. And we have essentially f concave up on -1 to infinity, and we have no inflection points. Okay, so seems like we're ready to sketch a graph here. We don't have a lot going on in this problem. So what did we see? We saw we had only starting at -1 here, and that was a vertical asymptote. And then we had an intercept at 0, 0, which also turned out to be a relative min. Now, we know that the function is concave up all the time, and it has to go to that vertical asymptote over here, so it really just goes up there. On the other end, the function goes off to infinity, so we really just have something like this. And so there is our function. In this case, there wasn't a lot going on, but that's what we get. This was a relative min. Okay, good.